distribute, I can email you those papers that I extracted.
Yeah, please do. Please do. And this inertia thing, I know I talked to Pete about it, so I'm glad that you're working on it and you're kind of getting some insights on the inertia impact. That's good. Okay. All right. Thanks, Kevin. So last time was a long ago that we started this, and last time we just basically talked about the distribution system, components of it, right? Substation, what's in there, regulators, transformers, capacitors, reclosers, and all that kind of good stuff that exists on the distribution side of the world. The next evolution, again, I'm trying to follow that guidance that Pete has put together in terms of what makes sense to cover in these lectures. He wanted me to talk a little bit about loads in general and load models and how does that apply to the distribution side of the world. So we'll talk a little bit about loads today. And okay, thanks. Then we'll talk a little bit about loads today. What is a load in general as we think of it on the distribution side. We'll talk a little bit about some of the terms that are associated with loads, peak load, peak demand, coincidental load, diversity factors, demand factors. We'll talk about some of that stuff. We'll talk about the current technology that we use around loads. So how do we actually get a lot of information about our loads, whether it's at a feeder level or a transformer level or a meter level, a single home level. And then we'll talk a little bit about zip models, some of the models that we use and we continue to use, used in the past, continue to use, especially in the absence of real data. So that's kind of what I wanted to chat about today and see if you guys got questions on it. You probably know this, and we have probably a lot of slides, and we missed some time early, so I don't want to go through a whole lot of basic definitions, but load to us on the distribution side can be defined by consumption on a feeder. So if I say it's a 5 megawatt feeder, that's load to me. That's how much load the feeder has. If I say it's a house, I can look at a peak demand or peak load on a house. I say that house is 1.5 kW at peak is what it consumes. So really general terms is what we use on the distribution side. Load characteristics, kind of in specific talk about the real and reactive behavior of the equipment or of the load as it relates to the distribution side. So this could be a piece of equipment. We could talk about a load characteristic of a computer, of a phone, or a load characteristic of a home, or again a load characteristics of a feeder, an entire feeder. So it really depends, right? We have also loads described in terms of classes. So the types of customers from a distribution perspective, we care about classes. So we can classify the types of loads that are connected on the distribution system. So we say this is a residential type load because you can probably model those in one specific way. They behave similarly. Industrial loads are a little bit different. Commercial loads are a little bit different. Agricultural loads are a little bit different. So the way we look at loads, we look at them in classes. So as a distribution engineer, I could look at my circuit and say, okay, it's made of 80% residential, 5% commercial, 5% industrial, and that tells me a little bit about the composition of my circuit and how I'm going to do some analysis on it based on that composition. So we really refer to loads a lot of times in terms of class.
Excuse me.
Yeah.
Why is that so important? So important to classify as the loads?
Sure, because their behavior is going to impact my understanding of the circuit. So, for example, industrial loads could be a 24/7 load. The load shape for it is not like your typical residential load where it peaks in the morning and in the afternoon, and then it valleys throughout the day. An industrial load could be running 24/7 operation. So the load itself, the characteristics, the way it behaves is different. Could be pulling a lot more VARs compared to my residential load. It's VAR needy compared to other residential loads. Also, its characteristics in terms of does it have a lot of motors and how it reacts to changes in voltage and deviation of voltage. So that's one of the things that we look at closely when we're looking at the distribution feeder, try to better understand what composition of loads do I have. And that way I just have a better understanding of what type of analysis I need to do when I'm studying the circuit. So we have models that try to tell us a little bit and predict for us what is going to happen to my system and how is it going to behave based on, again, deviations specific to voltage and frequency. So if voltage is going to change, what's going to happen? How is the load is going to react? Is it going to consume more energy? Is it going to consume less energy? Is the VAR characteristics going to be different? Typically what happens on the distribution side is I don't control a lot what happens on the transmission side. So I get a particular voltage that comes from transmission, right? I'm connected to a transmission bus, and I'm kind of bound by its voltage and its frequency that is fed to me. So as that voltage and frequency changes, I need to better understand how does that impact my circuits downstream. Is the voltage going to dip if I have a big dip in voltage, or if the voltage rises, how my loads are going to react? So a lot of times, if I don't have real data to better understand it, I'm going to rely on on models that are going to predict the behavior of the load. And again, residential is going to behave a little bit different than agriculture, than industrial. And we'll walk into that in detail when we talk about the zip models, characterizing what those would look like.
Because in the morning we usually follow some loads like mixture of some constant load, the constant current, or constant power. So whether you model those different categories of loads as that way. So because in modeling, when we usually build the load model as constant load or constant power or constant resistance, or a mixture of these loads in certain percentage. So in your simulation, how do you build the model?
It's very similar, very similar. So yeah, so
truly reflect the particular characteristics of that.
As much as possible. As much as possible. So yeah, we rely on the zip models specifically. That's the constant impedance, constant current, and constant power that you're talking about. And those are basic coefficients of what each of these equipment behind these classes would look like. So again, if I look at a house, right? The house will have computers, will have refrigerators, will have an oven. I know the equipment that typically exists inside a house. I will have a zip model for each one of these components, right? So we'll do a lot of research. We'll talk to a lot of manufacturers. We'll better understand what a zip model for a fridge is, what a typical zip model for a fridge would be. We'll know what a typical zip model for an oven would be, for a fan would be. And then we would know what a composition of a house would look like. Then if 80% of my load is going to be residential, then I know what my load is going to look like for 80% of my circuit. Then I look at my industrial. Okay, what type of industry is that? Is that manufacturing? Is that data center? Right? So based on that, I have a different zip model that I will put into my overall model. And that's how I aggregate. So I aggregate all my residentials based on a load. I aggregate all my industrials based on a load. That's if the engineer is really dedicated to the analysis. A lot of people don't have the time to go figure out that customer is at a data center or a manufacturer or an agricultural load. They don't have the time. They don't want to spend a lot of effort on it. So you end up with one general zip model for an industrial load. So he's industrial, and we'll say 10% constant impedance, 50% constant power, 40% constant current, and we'll run with it. So it really depends on how much time you have to dedicate, right? And how do you want to do things accurate and at least give you some decent results, not necessarily 100% accurate. And we'll talk about how this is all evolving. So the entire zip model thing is when you don't have a lot of data, right? AMI is going to change the world, and we'll talk a little bit about AMI. AMI is the automated meter infrastructure. That means I have real-time data coming off the meters every 5 minutes, every 10 minutes, every 15. That is going to change a whole lot about how we model and analyze our distribution systems today. We'll talk about it here in a second. This is just a basic example of data that we get on a load. So this is individual customer demand. And when I say demand, that's your kW consumption that's coming off that load, right? So this is one of the images that I got from that distribution system modeling book, the 4th edition, Kirsting's. Basically, it just shows time of day and then your kW demand on there. Typically, the meter will collect this every 15 minutes, 5 minutes, 10 minutes, depending on what the meter is. This is a 15-minute demand. So as the meter is collecting the kW, right, and it could be collecting kWh and doing some math internally to give you your kW, that's the instantaneous graph. we look at just what's your average over 15 minutes, and that's basically the value that I'm looking at. So right now I have a 4.6 kW is my 15-minute average for that time slot between 6:15 and 6:30. So over a day, I will have 15-minute intervals that show me what that load shape would look like for a given day, right? So for every customer, we would have daily load profiles that look like this that better explain to me what is that kW or that demand consumption for every customer that I have in my territory, right? Now, in the olden days, we didn't have this data for every customer. What we would is probably go and select a few customers, better understand their load profiles, and that way we can better anticipate how their behavior is going to look like. A lot of people use the kWh data. That's your basic consumption data because that's what we bill the customer on. So when you go pay your bill, that's based on your energy consumption, kWh, right? Then you can translate that into a demand profile that looks something like this. These are just some terminologies. So maximum demand, average demand, and load factor. Maximum demand is self-explanatory. Basically, what's the maximum kW value that I got in a day, right? So the maximum demand for that day is 6.18 kW. That's how much that customer has consumed over that day. I could have a maximum demand for a year, for a month, for a week, right? So I could say peak demand. So I would look at the absolute maximum amount of kW that a customer could have used. Average demand, again, self-explanatory, right? What is the average that the customer used over a certain period of time? That could be, again, over a day, over a month, over a year. Load factor is probably a little bit more interesting to explain, right? A load factor just tells you what is that average consumption ratio to your maximum consumption ratio, right? So on average, what is my average usage compared to my peak usage? Am I using the peak a lot, right? Or am I always using more of an average type of load, right? The load factor here is 0.4 for this customer. So on average, I use 2.46 kW, but I peak at 6.18. What that tells me is that the infrastructure that I have, right here, is got capability to provide 6.18 kW, but I'm not using the maximum capability of my facility, right? So I'm not always using all the potential kW that I could use from that facility. So I'm not using it to the max, meaning I'm only using 0.4% of its capacity on average. The higher the load factor is, that means I'm using my infrastructure overall to the maximum allowable limit. We'll talk about that when I'm talking about a total transformer here in a bit. Coincident demand, just the sum of demands for a group of loads, right, for the same time period. So if I have a group of customers fed off one transformer, so if this is a symbol for a transformer, I could have multiple customers living and being fed energy off of it. So this could be a house, 2, 3, and they're all fed off the same transformer, right? So the coincident demand is the sum of the demand for these loads at the same period of time. So I look at the same period, so I say at 5 p.m., right? And I basically sum up all the demands for these customers. That will be my coincident demand. The max coincident demand is the maximum of the sums here. All that is different is it's about a group of loads versus one particular load. The non-coincident demand does not care about the time interval. So I don't care about what is the time interval. I look at what is the maximum peak for each one of those. That will be my non-coincident demand, right? So the only difference between it and coincident looks at a specific time. So I look at 5 and I say, okay, what are my peaks at 5 o'clock? The non-coincident doesn't care about time. Just give me what is your peak overall. What were your peaks at all? Load diversity is just the difference between that max non-coincident demand and the coincident demand. So just how diversified is your load. Here's that example that I was talking about. So if I have a transformer feeds multiple customers, so you can think of those as single homes, all fed by the same transformer. These could be examples of that load profile for each customer, right? They're different. and each customer uses energy in a different way. You turn on a light, you turn on an oven. That's just how your energy is being consumed over a day. If I sum all those up, gives me that total transformer load profile. So if I'm looking for the transformer itself, what is the load profile for the transformer? It's really just the summation of all those 4 customers that are being fed off of it. Other terminologies, we call a demand factor, diversity factor, utilization factor. Really, again, they're all just terminologies that we use in the industry. And they're ratios of typically maximum, either coincident demand or non-coincident demand. And as you look at that, depending on what analyses you're trying to do. So a demand factor is maximum coincident to your connected load, right? So I look at the coincident demand, so the peaks at 5 o'clock, and I compare that to my connected load. And I try to better understand what does that demand look like? What does that factor look like? Diversity factor is the maximum of non-coincident demand to that coincident demand. So at any time, right, if I'm looking at the peak at any time, what does that look like for the overall peak? I figured maybe give you an example. So real numbers that we've got off some meters that we can probably look at a quick exercise on. So I'm not just talking terminology. So these are 3 transformers. Each transformer has a certain number of customers on it. So the first transformer has 5 customers. Second transformer has 6 customers. And third transformer has 7 customers on it. And these are the actual numbers that we've got for them for a specific time period. So I got a kWh, so that's the energy consumption, and kW is the demand, right? So that's the demand, average demand at that specific time period. And then I got there some demand factors. So these are the demand factors for each one of these transformers. Basically, I can calculate the non-coincident demand, right, for those. So non-coincident demand is what are the peaks, all right? What are the demands or the maximum demands of each one of these transformers by just summing those up for individual customers. So the first one, I just summed it up, 66 kW. But if I don't look at the coincident demand, all I have to do is just divide that by my demand factor, and I get that. It should be the diversity factor. You're right, not the connected load. Yeah, diversity factor. So these DFs, D5, D6, D7, that's the diversity factor that I got for each one of the transformers.
So if you don't, so diversity factor is maximum non-coincident by coincident, right?
Correct.
And you're calculating the coincident demand using the diversity factor. So how are you determining the diversity factor?
Yeah, so the diversity factor typically comes in either from surveys that we do for each customer, or again from real data that we would have collected over a period of time, and we've calculated these diversity factors. And we apply them to all the customers that we have in regions. So we do a lot of studies over the years, we do a lot of surveys over the years for a specific region. We say, okay, the diversity factor for this region on this transformer looks like this. Not a lot of science behind it. It's just how much data you were able to collect and how you're able to apply those diversity factors. But once I find my coincident demand, again, from just that calculation, I can apply a power factor to it and get my max diversified demand, right, in a kVA. The reason I look at kVA as an engineer is because my ratings on my equipment is typically in kVA. So if you remember from the very first lecture we talked about, transformers are typically rated by either kVA or MVA. So as a distribution engineer, I don't care about probably the individual meters, but my first asset that I put on the system is a transformer, right? So that's an asset that the utility owns. I go pay for the transformer, I go put up the transformer on the pole, and then I connect the transformer to my customer. So I care about this. So one of the very fundamental analysis that our engineers do is try to better understand how is the transformer holding up in terms of demand. Is it overloaded? Is it underloaded, right? What is the life expectancy of the transformer? Is it deteriorating? So we figure out if we need to replace it. Is it going to cause voltage problems to my customers, right? What is really going on with a transformer is one of the very basic studies that our engineers do. And that's kind of what they do. They look at its kVA nameplate rating, and then they look at the maximum diversified demand on that transformer, right? And then they figure out how does that compare to your kVA nameplate rating. Are you over that threshold, right? Are you overloading the transformer? Or you know you are within normal bounds and you're good to go and you are delivering servers to my customers just fine. So the way you do it is just, again, once you have the maximum diversified demand calculated, you compare that to your nameplate rating. So this transformer here, this could have a nameplate rating of 25 kVA. Right? That's what it's rated for. It can provide capacity of 25 kVA as a nameplate. We typically run underground transformers up to 130% of their nameplate. So we say they can, per manufacturer guidelines, we can load them all the way to 130%. Right? So on a 25 kVA transformer, that's 32.5. Makes sense? On overhead, the ones that are on top of the pole, so the 130% criteria is for underground transformers. For overhead, we can load them all the way to 170% of their nameplate rating. So we can go all the way to 170% of their rating without really damaging the transformer. So if you take a look at that first one, the first one, based on the data that we've got, the max diversified demand is 33.6. So I'm already crossing that threshold of 130%. Right? So if I continue to do that, I am truly going to start losing life expectancy on the transformer. So if this was a 15-year asset, right? So its lifetime, the transformer is 15 years. Every time I am above that 130% loading value, I am actually taking away life from the transformer, depending on temperature and depending on how long I'm doing this overloading for. I could actually calculate a loss of life percentage. So I can turn that into a year of life loss, a month of life loss, or a day of life loss on the transformer. Manufacturers typically give you a lot of that specification for you to use. So this type of analysis, this type of calculation is one of the very fundamental ones that we do at the utility. So our distribution engineers do this type of analysis almost every 6 months or every year on a collection of transformers that we've got in the territory. Yeah?
If you can consistently go that much above nameplate rating, what is the nameplate rating?
It just tells you the threshold, right? It just tells you the threshold of where you optimally need to be. Now, if you push it to 130% on top of the nameplate, you're still within okay boundaries without really killing the transformer or causing damage to the transformer. Why do they not put it at 130% already, right? Why isn't that the threshold? Why isn't 32.5 kVA the threshold? That's just an industry mindset or mentality. I really don't know how to answer that. That's what GE provides to us. That's what ABB provides to us. They give us a nameplate rating, and then they give us a max threshold on it.
Doesn't it also depend on the amount of time you're operating it at 130%? Like, you won't operate it at 130%
for the lifetime of the asset. Yeah. So that's what we're saying. 130% and above, so equal to or above, you start losing life on the asset. As long as you're below the 130% threshold, you are fine. You can operate it for 15 years. I think Jeff's question is why this nameplate is not 32.5. Why do you put 25? I really never understood the logic behind the industry doing that. Yeah. Even on regulators, this is not just a transformer kind of mindset. Even regulators, we have a nameplate capacity, and then we have a rating that we can cross or not. So yeah, I was never really able to answer that. Does this make sense? Just a simple exercise our engineers do on a consistent basis, try to figure out how are we doing in terms of our nameplate rating, and how are we crossing that 130 to 170%. And they can actually calculate, like I said, what they expect to have left on the life of the transformer. So it helps us from an asset management perspective. Right? When trying to manage all the transformers that we've got, millions of transformers that we've got, what are the life expectancy on those? And you can start actually drawing heat maps. Some of the sophisticated software tools that we've got today can do this analysis for you. You don't have to go plug it in by hand. So we'll talk about AMI and getting the data in real time. So you can start getting the data in real time and start calculating in real time what is the life expectancy of your transformer and get some kind of a heat map per circuit that says, okay, this is red, these transformers are in danger, this is green, transformers are doing fine. So AMI, and maybe I can take a quick minute and talk about AMI. So like I said, in the past, all we had was a meter that's spitting at the customer base. Then we'd send somebody to go and read what that reading was. So they'll go at the beginning of the month and read, the end of the month and read, and the delta between them is how much you consumed in terms of energy. Right? Put that on a paper somewhere, go back to the system, and that's how we build people. It's just you bill them at the end of the month by the delta, how much they consume. Kevin might know some of that stuff, but that's how the utility operated. Then they moved a little bit up, a notch a little bit, and they changed these meters to automated meter readers. So you stopped sending people out in the field. We call that AMR, automated meter reading, right? So we stopped sending people in the field, and we changed that meter with one that has a chip in it, and we'll send you its kWh value once a month. So you'll read that. You don't have to send it in the field. You started billing people off of that, right? So that started going in our database, and we started knowing a little bit more about our data. Then this got a little bit more advanced and changed into AMI, which is Advanced Meter Infrastructure. And this now, which is the meter that you see there on the screen, and everybody in Champaign today should have an AMI meter. So if you live in a house, go out and look in the back of your house where the meter is. It should look something like that, right? Should be yellow, should have a Landis and Gear text on it. Landis and Gear, it says there. And typically it's an AXRE or an AXRG. These are the acronyms for our type of meters that we've got. But that's an AMI meter. An AMI meter has two chips in it. Right? Two communication chips. One talks to the utility, to Ameren, and one talks to the customer, where you can actually talk to your meter. So the chip that talks to the utility brings back information like kW, which is demand, kWh, which is energy, amps, volts, power factor, temperature. All that stuff is being measured at the meter, and then is being sent back to the utility. So we can capture all that suite of data off the meter and bring it back. So imagine the leap that we have made from going in and just collecting kWh by hand to now getting all that information off your meter. This is actually a mesh network, radio mesh network. That's a proprietary, type of protocol that Landis and Gear has. And yeah, it's pretty much a radio frequency.
Do you know what spectrum they use?
I don't. Yeah, it's like I said, it's their own mesh network that they have. So they have collectors everywhere on our poles that basically talk. No.
Whatever company makes them.
Yes, this is their own. It's their own. Yep, it's not open protocol, and it's not a national spectrum that they use. Yeah, so they got their own mesh network. They install their own repeaters and collectors on poles. They ping the meters, collect that, and backhaul it back to the utility. Yeah. On the front end, that chip is a Zigbee chip, right? And that you can talk to it with your hand devices. So your home area network devices, you can go to Lowe's or Home Depot and buy one of those, or you can go online. Ameren has a program today that advertises those. So you can buy one of those for like $80. Sometimes you can get them for free. So you can go on Ameren's website and request some of these devices. You can come in and install it in your home. And these talk directly to the meter. Right? So they had the capability of going in, pinging the meter, and giving you some basic information off of it. What is your kW right now in real time? What is your kWh off the meter? A lot of times we have the capability of sending messages to the meter too. This is something that Ameren has not used yet or has not looked into yet. But a lot of utilities are starting to look into. We have the ability to send that message to the meter, and using those hand devices, you can actually receive that message. You can, through that Zigbee chip, receive that message. So let's say there's a tornado going on. We can send that message back to customers, say, hey, there's a storm, do X, Y, and Z, and you can display it on your home area device. The real futuristic stuff says I can send pricing signals to the meter. I can tell you what the price of energy is in real time. And then if you have a chip here that you can talk to it, forget about that just little hand device. Let your refrigerator talk to the meter. Let your washer and dryer talk to the meter. And now I know what the price is, and I can come on and off depending what the price is. You can program it. So you can tell your washer, don't come on unless the price is 3 cents a kilowatt hour. So you load it, go to bed, and I will keep pinging that meter until the price is within the threshold you told it, and it's going to come online. That's the real futuristic stuff that we think is going to happen at some time in the near future. So I just wanted to talk a little bit about these AMI meters that we've got. We've invested a lot as a utility in AMI because of these basic capabilities. But the most important capability that comes with AMI is, and some communities that don't have AMI still do that. So up to probably 3 years ago, if you lost power, you had to pick up the phone and call the utility and say, I lost power. Otherwise, the utility wouldn't really know, right? So I was always shocked. When I first got into the utility, I was absolutely shocked that I had to call Ameren and tell them I'm out of power. How does that work? You run the system. You own the system. You should know when I'm out of power. But they didn't. We didn't have the technology to figure out somebody was out of power unless they called. Or unless a big fault happened, like we said last time. If a big tree comes online and breaks a line, then you know an event happened. But if something happened in my backyard and something went bad and I'm out of power, I had to pick up the phone and call. Well, an AMI meter has that capability today. As soon as it loses power, it sends a loss of power message back to me, back to our systems. And I would know a customer has lost power. If 5 or 6 of them, say on like these 5, sent power loss signal to me, I would know something is wrong with a transformer, right? If a few neighbors down here on another transformer also sent signals and said, I've lost power, I know there's something probably wrong on the line itself. So we start to aggregate a lot of that information to start predicting where the problem is. And probably before the customer gets home or figure out that they've lost power, we've already sent somebody to the location to try to investigate what's going on. So this is one of probably the number one use cases that we have with the AMI and selling points for AMI is that we can get that outage notification right away. Another one, we can disconnect and connect a customer remotely via AMI. So in the past, if you wanted to change your apartment, you're moving from apartment X to apartment Z, I had to send somebody to disconnect your service while you're gone. So somebody's going to come in and disconnect your service. Or if somebody hasn't paid their bill for say 2 years and they're overdue on bills, I have to send somebody out to disconnect them. Right? They're not paying bills. You can do that all remotely today to disconnect and reconnect of customers. So saves on O&M, saves on that truck roll that I'm going to send somebody out of the field, and saves using that technology. So those typically are the 2 primary selling points for AMI on top of all that watts and volts and amps and stuff we get.
Ever get information like from the fire department if there's a gas leak to like disconnect a house remotely before they go in?
That's a great question. So everything we talked about here is electric. We just started the rolling out of AMI-like meters on the gas side. And which has that capability as well.
To turn off the gas, but I also meant to turn off the electricity so you wouldn't get a spark that would cost, because we had a house quite a few years ago just a block away blow up and
Sure. That's a great point. I don't think we've looked at that yet. To marry up, what makes sense. If you got a gas alarm, how do you actually disconnect it via electric? But that's a great point. Yeah, that's a great point. Maybe I'll ask about that. Yeah. Sure. Yeah, let me ask about that one. That's a good one. Yep.
But it can also report temperature, right?
Yes, it can. Yep, it can. That's basic temperature. What's the outside temperature, not necessarily temperature inside the home. These typically sit outside. Yeah.
Use of temperatures to do some analysis, the load varies with the temperatures.
Exactly. How do you correlate the temperature to the kW and maybe just build some correlation in terms of what you expect to happen at a particular temperature in the future? So you can build a trend, say every time it was 72 degrees, the average load was X. And in the future, you can build that correlation and say, okay, I expect load to be this value based on the correlation that I'm getting here.
So is the kind of value the customer themselves just be useful for the utility?
Yeah, I don't know. I mean, if a customer can get value of knowing what the temperature outside is, they could. They have access to it. But yeah, typically we focus on what can we gain from putting that infrastructure there.
Obviously, the real-time pricing.
Sure.
Check that at that time. Then temperature, what's the price look like?
Sure. You can. You absolutely can. Yeah. Okay. And then, so everything we talked about is data basic. So when I have the data, I am able to do a lot of these analyses, right? I'm able to calculate what the diversity factor is. I'm able to figure out what my coincident demand is. I'm able to do some analysis on my transformer. With AMI, that's going to be a lot easier, right? Because now I have the real-time data. I don't have to do any predictions, or I don't have to do any massaging to the load. AMI gives me direct data, and I can do direct analysis of a lot of the stuff that I'm doing. With the absence of AMI and AMR, when I don't have a lot of that data, and believe it or not, we've had AMI for 2 years at Ameren, and we still don't use it for the real-time analysis that I just described we could one day, right? So we don't use AMI to do load analysis and voltage drop analysis yet. So much data, we don't know how to integrate that with a lot of our analysis systems that we've got. Right? So what people do and have historically done is we use load models, either static load models or dynamic load models for our analysis. The basic components of the analysis that we use is that zip model that I talked about, and you kind of mentioned there, Kevin. Yeah. Right? Constant impedance, constant current, and constant power. Right? And this is just a quick graph that shows what these three are. The exponential load models, the point there, again, is to describe your active and reactive behavior, right, as voltage and frequency changes on the grid. Remember, we talked about I'm being fed a specific voltage and frequency comes from transmission, so I'm really at their mercy. Whatever voltage I get, whatever frequency I get, that's going to dictate the input to my loads. So I want to understand my behavior based on that voltage and frequency. So we use some of these exponential models, and they use those coefficients, right, to tell me about my sensitivities there. So if the exponent here was 2, right, I'm using a constant impedance model. If my exponent there was 1, it's a constant current, and if it's a 0, it's a constant power. Just makes sense, right? P, if it's constant, if all I'm going to get P, then that exponent is 0, right? If it's 1, I'm looking at a constant current, right? It's a linear function there. And if it's 2, I'm looking at a constant impedance.
But this load model cannot accurately reflect the characteristics of motor.
It does not. Correct.
You have some motor load, right?
Yeah, we do. And more detailed models can help you understand and analyze that, just like this one here. So this one here, this is the polynomial load model, right? And it's got a Z component, an I component, and a P component, right? These specifically describe now the behavior of every load that you might have. And this could be an experimental type of exercise that you can do. So there was a paper, and I think I've referenced it somewhere here. This one, experimental determination of the zip coefficients for modern residential commercial. Do you guys know? Oh, what's his name that works with Al Valdez? Who? No. I can see his face, and I can't remember his name. No, it's a tip of my tongue.
It's about the load.
Well, he participated in putting this paper together when he worked for Con Ed. McSomething, his last name. I can't remember his first name. Real nice guy. And he works, like I said, with Al's team. And he was on a couple of my DOE projects that we worked together on. But this paper, what they did is they went and bought all kinds of appliances. And they also went and tested devices inside commercial buildings. And basically, they were trying to determine these coefficients. What are the Z and the I and the P for every device that you've got? So as I change the voltage on the device, so they plug it in, right? They give it 120 nominal voltage, and they would calculate what the power behavior looked like, and would trend the power, and then calculate these coefficients. And they will change the voltage. They'll make it 125, right? And as you change that voltage, they will see how that changes your power consumption on it to better, again, understand what your Z and I and P components are. And they experimentally figured out each one of these components. So this truly can reflect, at the end of the day, what the expected behavior of each component could be, and then you aggregate those to, again, put them in more of a residential or commercial or agricultural type model.
So if they did refrigerators, do they get a cross-section of refrigerators and average them, or go, this is a new efficient one, this is an old one, or?
Yeah, that's a great question. I think they bought multiple, so they would have bought an old one and a new one. For lighting, for example, they did the fluorescent lighting, they did the CFL lighting, they did the LED lighting, and they will have a characteristic for each. For fridges, I think they bought three different ones, and they averaged them together. So they calculated the zip coefficient for a fridge based on these three that they bought. Fans, same thing. But things that are a little bit more detailed, like the lighting, they were able to break those down into their own components. Yeah. It's a very interesting paper, like I said, and it's available online. I don't think you have to be an IEEE member or anything. You just Google it and come up with a PDF. And like I said, I forget the gentleman's name that works with Al that participated on that paper. Richard McQuan. Yes, that's him. You know him?
Yeah, I'm working on a project.
Okay, yeah. He's a very good engineer, and he was one of those that was on this paper. So you might get some more information from him if you're interested.
So I have a question.
Yeah.
Do you guys take in these zip models? Do you guys take into, or are there any factors which consider the harmonic effects on the grid? Let's say there's a load which is polluting the voltage and current profile on the grid, and downstream there's a customer which I know there is IEEE norms which dictate that how much pollution can you create on the voltage and current profile. Let's say there's a hospital which needs a proper current and voltage profile. So in these load models, do you guys consider that effect?
The harmonic effect?
Yeah.
This is only on the fundamental component, not on the harmonic component. So not necessarily captured in this model. Harmonics is almost a separate world under the distribution system that folks study harmonics in a little bit different way. But no, this does not consider the harmonic impact.
So what do you guys do, like, in case there's an industrial load, and let's say there's an induction motor which is creating harmonics in that industry, and downstream you have a hospital or a clinic which for its devices to function properly, it needs a proper current and voltage profile. So what's the solution to that?
So first we got to get a complaint, right? So again, we don't have a lot of resolution on this. Somebody has to complain, and then typically what we do is start investigating. We put a power quality meter right at that customer premise, so at the industrial customer premise. And go ahead. No, go ahead.
So harmonics basically pollutes the power factor, right? And you can get the power factor from EMI. That's what you mean.
We could, yes.
So
yes.
You could technically analyze the power factor and study the load profiles because you already have a zip model of that load and kind of determine like how much of the power factor is getting affected due to harmonics.
Absolutely. We just don't have the manpower to do it. We're not really using the data yet today. So we just started. So everything we talked about on the AMI meter that's capable of being brought back. Our first initial use case started with just collecting KW and KWH. This was just for billing. I'm going to be able to bill accurately now, and I have some basic KW data. Then last year, we had a big project around voltage optimization to optimize the voltage on a feeder, and that was my number one use case. I said, aren't our meter capable of bringing back voltage? They said, yeah. Like, we want voltage on this. Well, we got to go spend money. We got to go change this. We got to start collecting. Where are you going to store the voltage data on every meter? Right? What is your use case for it? So we had to come up with a use case, an actual need to go pay for storage to store all that data that I'm going to collect on the voltage, and for how long you're going to store it, and what kind of analysis you're going to do on it. So I had a specific use case to use the voltage for. As we improve in our analysis to start collecting more and more of this data, right, we will get at this level of probably detail. But yeah, these are the use cases that somebody could be using this information for to analyze better, the service that we're giving to the customer. But if you don't, like I was telling you, we don't collect, for example, this is, you can collect this stuff. I'm not collecting it today. I'm not paying the money to go and collect it yet today. I have the capability to do it, but I'm not doing it.
Right now you guys just collect kilowatt hour and voltage.
And voltage, yes. And voltage, we just started going back to the meter. So the meter, you got to tell it what you want from it, right? So today we told every meter we want KW and KWH. To go back to the meter and tell it I need additional information, it's like reprogramming something. So I got to go send it a new program to start collecting. So we're going over air. So we're sending information to the meter to collect it. It's a very complicated process. because I don't want to impact the billing time. So if it's sending me kWh, I can't send it a profile that conflict and the meter will go bazooka. So it's a detailed process on when can you send the new profile to the meter and when can you start collecting data off of it. So it's a little bit more involved to practically do that stuff. And then again, to store a lot of this data and what do you do with it and where do you massage it and then who has access to it. You know, from a practicality perspective, we still are working through these things. As an engineer, sitting in your shoes, I always used to say, well, why not? Why can't you? But you know, as you get more in the real world, there's a lot of no's and why not to. Yeah. It's 5 o'clock, and I want to be mindful of everybody's time, so we can pick this up, you know, next class. And I wanted to just cover what a resistive load look like, what a typical zip coefficient for resistive load look like, what do the lightings look like, you know, typical large type of load profiles look like, and then how do we aggregate them? So remember, we break them down into industrial, commercial, residential, agriculture, right? These are my classes. Then for each one of those, so let's talk about the residential. The residential, this is what you find inside a residential home, right? A heating load, a cooling load, a lighting load, and some electronics. And then based on that, each one of those, we will have a zip model for. And then I aggregate those under one we call residential. That's how we run our analysis based on it. But maybe next time we'll talk a little bit deeper about it. Sounds good?
What software do you guys use to model?
Today our modeling software is called Synergy. It's a DNVGL product. If you guys have heard